First of all, thank you to also 51 and the union for making the stage to meet with you guys. I'm Bowen. I'm a staff research scientist from NVIDIA. And today I'm very glad to share some of our recent progress on building foundation models for robotic perception and its connection to other robotic policy or action. Now let's get started. First, let's take a look at the teaser video. So here's a beam picking task. Here's actually a collaboration between NVIDIA and Vention. So we helped them to build this fully autonomous system to perform the beam picking from the dense clutter, the industrial parts. The task is to autonomously detect the object, estimate the 60 poles, compute the optimal grasp, and then put the grasp the industrial part from the clutter, and then put it in a certain orientation on the conveying belt. So this will be like a part of the manufacturing pipeline where you want to put on the conveying belt and then send to the downstream. What is behind this? A couple of ingredients to make it work. First, this is a purely zero shot. Like these objects, we have never trained on these objects. Like we don't have the simulation or like a demonstration collection to perform imitation learning on these objects. So this policy is deployed purely zero shot on these objects. And also the reliability is actually very good. So in this video, it only shows the maybe first a few picking, but in the actual system, which if you have the chance to work with the Vention team, you will be able to see some of their live demos in some expo where they can show the robust beam picking from the beginning all the way until the end, until clearing the beam. Also, these objects are by themselves, they are very challenging because they are usually textureless. They also have some very tricky geometries. They're also very collision and a lot of physics, like the dynamics. When you reach the gripper, if it's not accurate, you may contact one of the objects, and that will cause some perturbation to all the rest of the objects, and that will also affect the shape of the clutter. So that will inversely affect the policy success. So behind this, how do we make this happen? So in the rest of the talk, I'm going to mainly talk about the 4 pillars. One is the depth sensing, the other is the state estimation, and also how we leverage these basic pillars to enable learning from human demonstration, and as well as how we build the real tool sim for the digital twin to enable sim and real robotic policy training as well as evaluation. First, let's take a look at the depth sensing. By the way, actually, I'm glad to see the first presenter presenting our NVIDIA technique on the Droid dataset. Actually, that is exactly the application of this work. Okay, so before we directly jump into the technique, let's first revisit the past progress. So stereo depth estimation is not a new problem. It has been there for decades. And if we revisit the very classical algorithm called SGM in 2005, if you apply them to the stereo images, the depth of heat map will look like this. And maybe it's not obvious how the original RGB image looked like, but later you will very easily tell. And this is the point cloud if we lift the depth into the 3D. So it's a very messy. For example, the textureless walls, that's usually the very challenging areas for the classical stereo algorithm. And later, as the deep learning era comes, we have the wrapped stereo. This is a method coming out in 2021. It is one of the milestones that transits the stereo estimation into the deep learning, like an AI-based method. If we lift them into the 3D point cloud, it may not be easily observable in the 2D heat map, but actually their geometries was still not great. For example, the walls were bent, the corners are not perpendicular, like we can very easily tell this from the humans. Also, there are still many floating points around the edges of the robotic arms. And by the way, up to now, maybe it's more clear to you what's the original RGB image. It's actually a snapshot of the robotic arm in a room and performing some calibration by gripping the calibration board. And what's different today is that with Foundation Stereo, by the way, this came out in last year. So here's the heat map, and here's the actual point cloud. We can see the significant difference from all the previous models. We can obtain very clean point cloud. The geometries are very sharp, and also even for the textureless wall areas, we're able to get very straight planes. And this model has been open sourced on GitHub, so feel free to try it out. It's very simple to run. You just need a stereo image. You can nowadays obtain that from a phone or like glasses or some AR headset. And of course, if you have a Robotic, that may be that may be even more familiar to you, because those are usually accessible from RealSense or Kinect, RealSense or Z cameras, those kind of sensors. And what's most important is that all of these results are zero shot. So unlike many of the methods that I will introduce later, like for those related works, they're usually performing the in-domain fine-tuning. So for the results we reported here, these are all zero shot. So basically, we wanted to build a one stereo model for all domains for the zero shot generalization. So here are some example results. It covers diverse scenarios like indoor, outdoor, objects of challenging properties like textureless, for example, the walls, the sink, and then the faucet, also reflective, translucent, and thin structured geometries, and also complex illuminations, for example, the reflections on the ground in the warehouse, and also some shadows in the street. Also, there are various viewing perspectives and sensing ranges. For example, some views are captured from the egocentric in the kitchen, and some are from the exocentric, some are from the mobile robot from the ground in the warehouse, or some are from the street. I don't have enough time to dive into the details, but I will just briefly mention the recipe for making things work. First is the high fidelity simulation. So at NVIDIA, we have this unique strength of using the Omniverse to render very high fidelity synthetic data. So this simulation, in the simulation, we have the privileged information to very easily generate large quantity of data and also the perfect ground truth. Another thing is it's also a good timing to revisit the stereo depth estimation, because we can leverage the latest progress on monocular prior. So monocular depth estimation, some of you working on computer vision may be also familiar. Nowadays, monocular depth estimation has made a lot of progress, and some of them have been claimed to be metric scale. However, for the monocular depth estimation, it's still the metric scale estimation is still based on the best educated guess. So there's no way to really guarantee the actual metric scale. However, in the stereo setup, we have the extrinsics, basically the baseline between the two cameras, to obtain the exact metric scale. But they are not like one way or the other. So we build on top of the monocular priors so that the stereo matching can perform better on some ill-structured places, like the translucent surface or textureless areas. And finally, given the high fidelity simulation with a large quantity of data and also the monocular priors, we build a scalable architecture to make the better use of all these data and priors. So here are some other results. Again, this is also happens to be a joy dataset. I swear I have never seen the slides from the first speaker. So this is also the joy dataset. We compare with some recent papers published in the top venues like ICCV, CPR. So we can see there are a couple of challenges in this scenario. For example, for the microwave, it has a very dark black door, and also the translucent and the glossy surfaces. And also the entire illumination in the room is also kind of complex. There are some dark areas, but there are also some overexposure from the window regions. Regardless, we can achieve very good depth map. And the difference will be more obvious if we lift them into the 3D point cloud. So if we visualize in the 3D point cloud, we can see, especially at the coffee machine area, like we can obtain very sharp, and a flat table plane. And also for the background of the room, we can also reconstruct it like nicely. Another question, some people working on the relative domains may be wondering, like, how does that compare to let's say the RGBD cameras. So here are some examples. For example, we compare with some commonly used sensors, including the RealSense, ZAD. So here's one example of the knot. So you can see in the RealSense, the point cloud of the table is actually very fluctuated, and also because of the nature of these consumer depth cameras, they usually have some holes in the depth image. And the Z Mini is another stereo-based depth estimation method, but we can still see like the plane is not even. Here's another example on the toolbox on the text on the blanket. So we can clearly see the boundary of these different objects when we rotate to different viewing angles. And this one is there's even more differentiable difference, like the strong reflections of all these dense screws are causing issues for the RealSense and the Z. And also, if just looking at one bolt, the reflection is causing these challenges. So these are the typical challenges, like the reflections and the textureless areas. So the good thing is that right now we have the Foundation-Stereo, which is very strongly generalizable. You can basically apply it in zero shot without worrying about collecting your own data and then fine-tuning that. However, one issue is that they are not real time. Here I'm placing Foundation-Stereo and another concurrent work master. They are both aiming for strong, like a zero-shot generalization, but they're never close to running in real time. Just to give a sense, so they are maybe running in the magnitude of 1 second per image. But if we want to apply it to robotics or other real-time systems, usually the real-time will require like 30 Hertz. On the other side, the real-time lightweight stereo depth estimation has been active also for many years. And there are some related works like the LED stereo, BANet, and RT-gap, IGAP. The good thing is that they can run very high frame rates with a very lightweight backbone and the network designs. However, they are still very far away from being able to run zero shot. Like whenever you grab these models, if you just run them out of the box, it will probably disappoint you. So that means they usually depend on the target domain fine-tuning. And the tricky thing is that for the depth, it's very hard to do fine-tuning because it's very hard to collect the data with the very accurate pixel-wise dense depth map to perform the fine-tuning. So this is something different from if you work on object detection or segmentation, you can hire some human to annotate. But for this kind of ground truth, it's almost impossible to annotate with a human. So can we do something to combine them together? So that it motivates us to work on the Fast-FoundationStereo. And actually, we just presented this work in CVPR in the last month. So this is a real-time and a zero-shot stereo matching. So remember the two aspects. One is the real-time, and the other is the zero-shot. So we wanted to bridge the gap between the two almost impossible axes. So here's a plot. If we put every method in the same, the vertical axis is the generalization arrow. The lower is the better, and the horizontal axis is the speed. So FPS, the larger is the faster. Ideally, we want the model to be more on the right side, but on the bottom. So we have a fast and a low arrow model. Foundation-Stereo is on the very bottom left, the cross. It has a very low generalization arrow, but at the same time, it's also pretty slow. Similarly, are some concurrent works like the Monster, which I just talked about a couple of minutes ago. The stars are our Fast-FoundationStereo. So, and one thing to note is that you will see multiple stars. This is because the Fast-FoundationStereo is actually a family of models. It's not just a single model. We had some recipe to search different trade-offs between the runtime and the accuracy. So here we can see for this first group, which means without the tensor RT acceleration, there's already a very obvious push from the Foundation-Stereo, like one Hertz or so to like 20 to about 40 Hertz. And then with tensor RT acceleration, for each of the stars, we can then push them further on the right side. So by the way, just to give some background, tensor RT is a NVIDIA acceleration technique for the deep learning models. So we can see that it can bring another like a 2x speed up from the 20 to 40, and for those originally like a 35, we can now able to achieve like around 70 to 80. So this is this can satisfy our real-time speed, which is usually like 30 FPS if we want to deploy on some real-time applications. And just to give a more concrete idea of the visualizations, so this is our Fast-FoundationStereo. We are still using the similar image I demonstrated a couple slides ago, and here's the Foundation-Stereo. So we can see if we compare these two depth maps together, and also including the point cloud, we can see there is not much performance degradation. Again, this is Fast-FoundationStereo, and now we're sliding to the Foundation-Stereo. And just a note, given this tiny, by the way, this is the RTI gap, which is another real-time model, but as you can see, they cannot be easily applicable out of the box. And just to reiterate, this is with like a minor performance difference, like accuracy difference, but the speed is more than 10x from the original Foundation-Stereo. And also, we're showing some lab demos here, just to explain the setup. Here's the Z camera, which is a stereo camera. And on the computer screen, we're doing a couple things. First, we stream the Z camera to the box, and then we run Fast-FoundationStereo to generate the depth and the point cloud. And then we are displaying them for visualization on the screen. So you can see the bottom left is the RGB, and then the top left is the depth map from the Fast-FoundationStereo, and the point cloud is the lifted version. And the entire screen you are seeing is just a font capture of the entire process. The process is live, so whenever we see the user is performing some actions, it's almost immediately reflected on the computer screen. And in the following, we're demonstrating a couple of different objects. First one is the hammer, which has this thin handle, and we can see the handle area is very clearly like distinguished on the depth map, and also the point cloud. And next one, we are seeing a peanut butter bottle. So this is kind of translucent, although not entirely, but it also has this textureless issues, for example, the totally brown areas. It's also a circular shape, so if we zoom into the point cloud, we can actually see the point cloud is almost perfectly circular. That implies that the point cloud is geometrically correct. Another thing is the font. So this is a very challenging object because this is totally black. And actually, one interesting thing is that when the phone is facing to this stereo camera, there are some reflections. This is the actual image fed into the Fast-FoundationStereo. So there is a strong reflections of the ceiling light. But despite this challenge, the depth map is not like a hurt. And also from point cloud, we can clearly see the planar surface of the phone. And lastly, we're also doing the human head. And we're also working with many robotic data collection companies, because nowadays it's very popular for collecting egocentric or human manipulation data. And many customers have been using the Foundation-Stereo to obtain the point cloud of the hand and then register the hand pose, for example, manual hand to the Foundation-Stereo depth. Here we're just demonstrating we can continue to use this process with the Fast-FoundationStereo in real-time speed. And also finally the door, which it has the purely white texture and the very complex shapes. Another interesting thing is that in Fast-FoundationStereo or Foundation-Stereo, we didn't really reinforce the cross-frame temporal consistency. And when we run the Fast-FoundationStereo, this is actually frame by frame. And thanks to the real-time speed, it's able to keep up the real time. However, we didn't reinforce the temporal consistency. But as we can see in the results, it actually, for the most part, is temporally stable. So that actually implies the model's robustness is also is also good. The stability. Okay, so far we have talked about the depth sensing, and next we're going to move on to the state estimation. So this is about our foundation pose, which is earlier work before the FoundationStereo, which we presented in CPR 2023. So the TLDR is a zero-shot object 60 pose estimation and tracking method, and also it's open source on the GitHub. So feel free to take a look. So just to explain the problem setup. Basically, for example, when we want to perform robotic manipulation or for some applications, we want to know the object position as well as its orientation. For example, one application I just showed earlier in the slide is that we want to pick up the industrial part from the beam, but also place the industrial part in a certain orientation. Another motivating example is that we want to, for example, for some robot working in the supermarket, we want to place the bottles on the shelf and making them very aligned in a certain orientation. So the goal is to estimate the position and orientation. But in the past, many of the models they needed the per instance training, which means for the exact can or the exact bottle, I need to first train on that data and then estimate the position or orientation for that data. So this may be a bit surprising to you because we have seen a lot of object detection or segmentation that you don't really need to train on this human or this object to be able to detect it. However, for the pose estimation, that was just the truth before this, and so we wanted to make a change for that. So in foundation pose, we wanted to perform zero shot. So whenever we want to apply to the new model, we want to skip the retraining process. A couple of things. First, we can support multiple scenarios. One is, for example, model-free reference images. For example, we have a few images of these objects, and then we can to do a quick onboarding, and then we can estimate the pose of the object in a different scene. Or in another scenario for the industrial, usually if we have the texture, the 3D model, for example, the CAD model or 3D asset, we could also immediately apply the pose estimation. It can also support the pose estimation, which means we run frame by frame, or the pose tracking, which is faster and also ensures better temporal consistency. And there are three characteristics. First is versatile. Like I said, it supports in total 4 different setups, and also it outperforms all the specialized models. So in this radar plot, each of the method only supports one of the 4 setups, but we actually outperform each of them in all the 4 tasks. And finally, this model is actually purely trained on the synthetic data, but it surprisingly generalizes to the real world. Here's just another example of the version we showed before, but some more detailed visualization. Here we're actually showing one possible pipeline by combining FoundationStereo with foundation pose. So on the right side, we are seeing the point cloud from the densely clouded beam. We can see from the point cloud is very, first of all, the point cloud is sharp. We can see the dense pile very clearly. And also, we can perform the pose estimation. And the red is the estimated pose of that part. So this is overlaying the CAD model onto the original point cloud. So just to clarify, this is not a segmented point cloud. So that's why you are seeing the original color, but also the transformation, the transform the 3D asset onto the scene. And on the bottom left, we're seeing some poses visualizing the bounding boxes. So for these bounding boxes, it not only have the positions, but also the orientations. So all the orientations are exactly aligned with the whole of the industrial part. Some other applications. This is just a demo I captured. For example, for the driller, this is just a driller. I didn't find the asset. I just scanned it with some phone app, and then I can immediately perform the tracking with that. So we can see actually when I initially pick up the driller, there was some occlusions from the hand and also fast motions and rotations. But regardless of that, the tracking is quite stable. And also I manipulate the driller into different rotations. And lastly, when I move the hand, actually I was capturing the recording, but I didn't realize that my hand is actually almost fully occluding the driller. But interestingly, the model is robust enough to handle that. Another application is the AR. For example, when I pick up the book, I can turn the book into a game controller. Again, this is a new book that I've never done, have never been trained by the model. So I'm controlling. So the bottom right shows the original video recording, and the main screen shows the tiny like AR game. So I'm using the book as a 6-off game controller. If you have ever played like the Oculus, you must know the game controller can handle the 6-off. And here I'm just using a random object for that purpose. And then I can perform the simulation. Like imagine I'm just purely controlling the board, and then the metal ball inside of the board is purely driven by the gravity. And it can perform the mesh, collision, and physics simulation with the given the pose of the wooden board. And just to reiterate what makes this possible, first, this is a 460 pose estimation and tracking. So there is tracking, so it has to be accurate, robust, and smooth for the physics simulation. Otherwise, if you see some jittering, then sometimes the wooden board will jump back and forth and then maybe even penetrate with the metal ball. So that will make the physics simulation crash. So obviously we need to make the tracking robust and smooth. And also the speed has to be fast for real-time performance. And also this is a very random book. So the model is just applied out of the box with the generalization. There are many more applications. I'm not able to enumerate all of them, but here are some that we at NVIDIA worked with some other companies. For example, the industrial part on the top left, there is an L-shaped bracket. It's very metallic, and also some pallet. For example, in some warehouse, some companies are doing the forklift manipulation for the pallets. They want to estimate the pose for the pallet and then interact it with the forklift. Also some docking, for example, this is just an experiment for docking the mobile robot. And also the Yaskawa, we worked with Yaskawa from Japan at the GDC, and they're working on the like a package manipulation with the robot, and these are all running with the foundation post. This is kind of similar to the beam picking example I showed earlier. Now, after this, let's take a look at the learning from the human demonstration. That involves our recent work also published in CPR that we presented last month. So this is the TLDR is a zero-shot for the reconstruction of human object interaction from the monocular RGB videos. So in all of the sub-video, in each of the group, on the left shows the original video, which is actually a YouTube video. On the right, we show the human object reconstruction. So the motivation is that if we can, people have seen the success of GPT, Gemini, and also the agent. And then one of the secret sources, they are able to leverage the internet scale. But for robotics, we don't yet have the luxury to leverage that. People are using that teleoperation doing the per environment data collection, which is like a very baby step compared to the internet scale. So the motivation is like, how can we push forward to really extract some meaningful information from the internet scale? If we can later apply this to the YouTube level or any video, we can hopefully extract the interaction files of how humans manipulate these objects. Inspired by that, we also have this learning from demonstration work. So here is basically we're performing the few short learning from the human demonstration. Unlike some of the traditional, standard diffusion policy or VLA, which usually requires tens or hundreds of demonstrations. Here, we just wanted to see how can we leverage just a few short, less than 10 demonstrations. And the recipe here is that we are taking for example, taking a video recording of how humans perform the boring task, and then we can reconstruct the entire motion sequence of the task. For example, there's a kettle pouring the water into the mug, so we use the foundation pose to estimate the pose trajectories. So basically the translating from the human demonstration to the robot policy is basically replaying the motion to make sure the task is successful, regardless of the embodiment gap. Once we train this model, the model can learn, given the current state, what's the next step. So on the right-hand side, it shows this process, like whenever, at each time step, the colored point cloud is the actual observation, and the gray one is the prediction of the diffusion model on what's the next step to place this cattle to perform the task. And obviously, as a human, we can always imagine how I should pour the cattle to perform the task. And so we do this step-by-step diffusion-based prediction to let the robot always follow that trajectory. So the policy will just turn into this path-following formulation. It actually turns out to work reasonably across different environments. Actually, there are different tasks shown here, like putting the log onto the coaster, and also putting the plant into this more tolerated, like a more tighter tolerated the vase, and also the water pouring. So this is also not easily solvable by just a scripted policy, because for this pouring task, especially, it's very hard to specify at what time, at each time step, how many degrees you rotate and how many translations do you move. So it's a very tedious process to, if you want to script a policy for the to make it work. But here we're using a data-driven way, but it's also a very efficient data-driven method to do the learning from demonstration. Another work is our very recent one, like learning back source manipulation using context range guidance from human demonstration. So on the very left, we're showing the human demonstration on how to interact with this articulated object. And the middle one is the learn the policy in your simulation. And finally, we're also showing how this learn the policy can be transferred to the real world. The key idea is to transfer the human manipulation skill to the dexterous robot policy through the object-centric context range. So in the past, many of the RL algorithms rely on the reward designed around the position of the contact. But here we're also reasoning the range, basically the force direction around the contact, so that the learning is more efficient and effective. Given the time constraint, I'm going to also briefly talk about our final pillar, the real-to-sim. So this is a recent work on a modular and automated scene generation for the policy learning and the evaluation. So basically, given the input of video of the real-world scene, we can automatically turn into an interactive simulation. So here's the original video that you will capture in the real world. And then we're going to turn into a digital twin in the simulation. So later, the robot can perform training or evaluation in this environment. Another example, here we have the very dense cluttered table. We can turn into an interactable digital twin. So why do we do the simulation? The benefit is that for the robot to work on the real world, there are many constraints. For example, if you want to collect the demonstration, you have to obey the physics, like the velocity you move has to make sure it's safe, and also it's constrained by the robot hardware. But if we can make things work in the simulation, we can even distribute the multiple different environments in parallel. We can also accelerate the time step. So making things work in the simulation will be reduce a lot of pain that will meet in the real world. Here on the right plot shows the correlation between the success rate if we evaluate the policy between the sim and real. Horizontal axis is the real world success rate, and the vertical axis is the simulation success rate. We studied a couple popular models, like including Pi 0.5 and also Groot N series model from NVIDIA. And there are many different tasks represented by different shapes. And so if the correlation between the sim and real is along the diagonal, that's a good thing. That means your simulation is very representative for the real world. So if it's really close to 1, then you can just solely rely on the simulation to tell if your robot policy is good or not. So for some people not working on physical AI, there's one thing different from purely software, that whenever you train a deep learning model, it's not so easy to evaluate the model just in the software, because you can just use data to evaluate. It's very quick, it's automated. Nowadays, it's even simpler with agent. But in the physical AI, if you want to evaluate the policy, you have to roll out the policy on the real-world robot. You have to set up the scene, for example. You have to set up the layouts of the scene, and you need to wait for the rollout of, like, basically the motion or the action for the robot to finish. So that's a very, very tedious process. So if we can just move everything to the simulation, then we can skip all that process. Here are some other examples. For example, we can also do sim-to-real policy training. So we can perform the training in the simulation and transfer to the real world. For example, the bottom, for example, in the simulation eval, the success rate is 100% in the real world, and the success rate is 92% in the simulation. So they're pretty close. And the good thing is that in the real world, the success rate is even slightly higher. Also, there are also involve some tasks like stacking the dishes, etc. I think we are on top of the time. And thank you for your attention. And here's my contact. I'm happy to connect, and I'm happy to take questions.